So just to check for comprehension, what I'd like you to do is to respond to the chat window I'm about to post. Instead of replying to everyone, however, what I'd like you to do in the to option with the pull down that shows everyone, I want you to hit the pull down and then select my name specifically. Here's the question that I want you to respond to. Is a series circuit more an example of a physical and, or is it a physical example of an or? And again, I want you to respond only, okay? So what I'd like you to do is to respond to me only. Everybody understand? So everyone is responding to the prompt in the chat window, but responding to me only as the instructor and not to everyone. What we want to do is see what responses we're getting. So in the next 30 seconds, I need you to respond to whether or not a series logic gate is more like an and or an or. Is a series logic gate, I'm sorry, a series circuit. I meant to say circuit, right? Did I not say that? Is a series circuit an example of a physical and, or is it a physical example of an or? And that's what we're responding to. Okay. All right. So got about 10 more seconds. Only 3 have responded. I need everybody to respond. Choose one or the other. But think about it. If you have a series circuit, that means you have 2 switches, one after another. That's what we talked about last Friday. Is it an example of an and or an or logic gate? Please respond to me directly. Okay, I've got 5 out of 9 people responding. So if you would, go ahead. If you have a series circuit with 2 switches, one after another, on a single loop of physical wire, is that an example of an and or an or? Please respond to me only. Only 5 students have responded out of 11. So I need a few more of you to respond. So counting myself, and that's who I want you to respond to. We need 6 people to respond to that question in the chat. Is a series circuit a physical example of an and logic gate or an or logic gate? Okay. All righty then. Here's your answer. Can everyone see my screen?
Yes.
Yes.
A series circuit where one switch follows another, unless both are closed, unless both are turned on, the output is always false, right? So that's a physical version of the and logic gate. If you answered and, excellent. If you answered or, here's the or. It's in parallel, it's not in series, and either one of them being on will close the circuit. And the output is one and the same with an OR logic gate. So remember, parallel is OR, series is AND. This is something we want you to understand intuitively by the end of this module. Also, it's just a reminder, I did have a mistake on the module 2 assessment. It said that you had to have that done your first attempt by the 5th of October, but it stated Monday. And I've since corrected that so it reads Wednesday. So please make sure you have your first attempt of your module 2 assessment in place by 10 a.m. We won't be able to extend past that point. I'm almost ready to post the final version of the module 1 assessment. That's the other thing that you need to complete by 10 a.m. Wednesday. Any questions about what's expected by 10 a.m. Wednesday? The final attempt of the module 1 assessment, the first attempt of the module 2 assessment. Okay. So we were talking about differential versus universal applications. So in a differential application of a NOT, that's usually on the input side. A universal application of a NOT to a basic logic gate is usually on the output side. Why do I say usually? You can put a NOT here in front of the B input, for lack of a better label, right? So if this were the A input, you have a NOT that's going to flip the input of A for this AND logic gate, and this is a crude drawing. But if we put another NOT here, another NOT there, and another NOT there, that would be the same as putting a NOT in front with that open circle, right? In this case, it's a NOR, right? So what you're seeing here is a NOR, but if it was rounded, that would be a NAND. Any questions about how differential typically involves inputs? Universal typically includes, I mean, it's applied by the output. Any questions? So this is, can everyone see my screen?
Yeah.
Okay, so in your textbook, in that first chapter, Nissan and Shakin talk about an XOR. An XOR is built with an OR, and it's the last logic gate that receives input before the inputs are processed and passed out of an XOR, which is one of the reasons why OR is a prominent part of the name, okay? So the XOR logic gate is a game changer. The XOR logic gate is an innovation that allows for a lot of very important functions in networking and in cybersecurity with encryption, okay? XOR is an amazing logic gate because it helps you identify whether or not all the inputs are the same or all the inputs are different. And when you read, if you go back in our module 3 reading assignment, it asks you to read some more of the same thing. And now as you're reading it again, there are some light bulbs that should come off, and you're seeing the W1 and the W2, and you go, oh, I know what that is, because it's what we did in our solution for module 2. Oh, I know what this not be. The wire isn't called W1. The author has chosen to call this W1 input not B, so as to distinguish it from the other wire outputs, okay? So that's what you're seeing here. And I wanted to call that out intentionally to you. We could have said W1, W2, W3, W4. But in order to be more descriptive with the wire label, the author chose to use not B because this wire is split. So I want to explain this and walk through this. Once again, the OR logic gate is the last to receive input, so it's one reason why the name, the custom name for this composite logic gate has OR in the title, right? And there are two ands, and then the knots are differentially applied to each of those two ands. So we have output from and, the first and the second and that feeds into wire 1 and wire 2, and that becomes the A and B of OR. Everybody good on this part of it so far?
Yeah.
Okay. It's here where it gets sticky. With an XOR, the A input in this design, and there are different designs to create an XOR, but in this design for the XOR, this convention here means there's a fork in the wire. The wire is split. So the wire diverges, it continues straight into the A input, the top input of the top and, or the first and. So it's the A input of the first and that wire is continuous. But on the way in, it splits. Everybody see this? It splits. And there's a fork that comes down, and this A also feeds the top input or the A input of the second and or bottom and. Now there's one other thing that I want to show you. There's a little hump right here. It's kind of hard to see, but it's easier to see in the textbook. Does everybody see that little hill, that teeny tiny little bulge right there?
Yeah.
So the wire is coming down to feed into the top input of the second and it's overlaid on top. It's overlaid on top of the B wire that's forked up to feed into the B of the top and. So we're laying the wire down physically over on top of the other wire, and here's the knot. And the output of the knot for the A, we're going to label that wire knot A. So the value of A comes in and it's flipped. And what is the output of that is called knot A. Kind of makes sense when you think about it. It's like, okay, I have A input, and if I feed in, 0, 0, 0, or I feed in 0, 0, and 1, 1 in succession with my truth table, because we have two inputs, we have a 4-row truth table. The A inputs are 0, 0, and 1, 1, and then in the B column, it's 0, 1, 0, 1. I hope everybody knows what I'm talking about at this point. If you don't know what I'm talking about at this point, I would urge you to schedule an appointment so we can cover some ground that you may have missed in previous classes and previous modules. But okay, so we have this separate A input that's flipped with a knot, and it becomes the input for the top input of the second and. Now, in the bottom, we have the same thing, only in reverse. We have the B input funneling straight into the lower input of the second and, the lower and. Everybody straight with me there?
Yeah.
Okay. As it's coming into the XOR, it's forked or split. And that wire comes up, and that wire is laid under the other wire that's laid over top, and it comes into the B input for the top and, but before it reaches the B input of the top and, it's flipped with a knot. And the output of this one is called knot B. That's how the author chooses to label this wire. So this wire carries knot B output, if that makes sense. So that's fed into the second input of the top and. And works like and does. And takes the differentially changed knots and it just does what and always does. If there's a single zero in the mix, the output is 0. So when you look at the truth table for an XOR, you get something really peculiar. Basically what you get is a way to identify when inputs are different or the same. What do I mean? The truth table for an XOR, we can follow the truth table for the XOR and it'll tell us what happens. But basically when all of the inputs are the same, as in all the inputs are zeros or all the inputs are 1 versus all the inputs are different, it lights up and turns on, I believe, when the inputs are different. Let's verify that. I'm going to go into our textbook just because it's something that's good to do every now and then. Everybody with us so far?
Yeah.
Yeah.
Okay. Everybody has a copy of their textbook, right?
Yes.
Yeah.
Okay. So this is the first edition, but it's very much like the so I'm going to go ahead and I want you to notice when the A and B inputs are the same, the output is false. But when there's a different input, put another way, the XOR is a great way of determining whether or not inputs are different. Notice here in the truth table, when A is 0 and B is 1, the output is true. When the reverse is the case, when A is 1 and B is 0, the output is true. Now, what happens if we have an XOR with 16 inputs? If just a single input is different, the output is 1. What am I saying? 15 out of 16 inputs on a 16 input XOR, 16-bit input, 32-bit input, 64-bit, it scales up, right? You have a 64-bit computer, you have a monster, you have a beast, right? A 64-bit computer is an amazing innovation compared to an 8-bit or 16-bit or a 32-bit. But never mind that. If you have networking issues or encryption challenges when it comes to cybersecurity, the XOR is uniquely qualified to flag or identify. It posts a true when any of the inputs are different. So you could have 15 out of 16 that are false. And if there's a single 16th input that's true, it'll say, whoop, hey, we have different inputs here. Now, why is that valued? There are times, digitally speaking, you want to detect whether inputs differ. If inputs are different, it could be a safety circuit in a rocket or a satellite or a laser weapon. Is everybody listening?
Yes, laser.
Yeah, laser weapon, right? If some of the inputs are different, the output of an XOR, let's say we have an 8-bit XOR, I'm just giving you a hypothetical, and there are safety circuits that are designed for the laser weapon, and it's not going to fire if there's a fault, if there's an issue. You get a go, yeah, I'm good, this is good, this is good, this is good. I have a 1, thumbs up, the power supply is good, the capacitor is good, the mirrors are good, the blah, 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 right? Okay, so maybe we're not using mirrors nowadays, we're using digital LEDs to generate laser impulses. Regardless, Yes, 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 yes. Oops, here's something that isn't. Bing, we have an error condition. We can't fire the weapon, right? So that's just one reason why XOR is so magical and, I mean, mythical proportions. It identifies when inputs differ in any way whatsoever. So it could be a mix. You could have a split where 8 of the input, 4 of the inputs are true and 4 of the inputs are false. It's going to come out with 1. Where do you get a false? When all the inputs are the same. So if all 8 inputs are 0, the output is false. If all inputs are 1, the output is false. So in that laser weapon scenario, you could have, in that safety circuit, everything is true, 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 true. All the safeties are intact. You have 8 ones fed into that 8 input XOR. And what you get is, nope, we don't have an error condition. Error condition off. It's a condition you can test for. Does everybody understand what we're talking about?
Yeah.
Now, I hope you go back and you reread your textbook. As we keep going into the modules, I hope you go back over the same material, because what you're going to find is like you get deeper in layers of your understanding, and that's actually a very cool thing. If we had a chip fabrication shop in our home garage, right, the author talks about very rich examples of how this stuff matters. And the first time you read it with limited knowledge, it's like, okay, half of this makes sense. The other side is, it's all Greek to me. Read it again. Now it makes more sense, right? And you go back, you're like, oh, I've seen this before. No, you haven't. You haven't seen this before with new understanding. Okay? This is how you crunch and munch the most complex research material on the planet. This process I just explained. It's a life skill, okay? I hope you'll consider it. Anyway, any questions about this before we move on in our study guide? So the XOR, you want to study the XOR, you want to be able to recognize this from scratch. In your next module assessment, I'm going to ask you to identify, this is the interface view of a very special complex logic gate. What is it? And you're going to go, oh, I've seen this before. Now, if you click some of the links in this study guide, what you're going to find is that there are some websites that show you different ways of creating the XOR, right? So there's a different schematic, a different implementation to create that XOR. And you want to be able to recognize this primary version of it, but also alternate versions. All right, moving right along. Any questions before we move on from XOR? Going once. Okay. So the MUX and DMUX. MUX is an acronym, MUX, which stands for multiplexer. I should probably underline this so that you get what's going on here. But when somebody says a MUX, they're talking about a multiplexer. It is another innovation that changed our world. A multiplexer logic gate allows you to select different inputs. So what am I saying? Does everybody see this right here?
Yeah.
Okay, remember that the first in hardware, the first component in hardware is always numbered what?
0.
0, right? Thank you. So this is I sub 0 or I naught. Everybody say I naught.
I not.
I not.
Yeah, now in the physical sciences, a lot of times, or in the military, they'll look at 0 and they'll call it naught, right? Well, that gets to be problematic when we're talking about logic gates, that can be confusing, right? Which is why it would be better to call this I sub 0, like the Mortal Kombat character Sub-Zero, right? I sub 0. And that's just to avoid needless confusion. Let's pretend that we have two different inputs and we want to be able to select or switch. We want to select or switch between one input and another. Let's pretend that in this complex logic gate, I have I sub 0, or what would this be called by the same type of expression? Anyone?
I sub 1.
I sub 1 is correct. Thank you. Yes, I sub 1. So what's happening here is that there is this element here. Based on this element, depending on the input here, you're telling this logic gate, okay, I want you to use I sub 0. And then if you change the input for A, I sub 1. Put another way, you're able to intentionally switch between different inputs. You can select between different inputs given a certain scenario. Well, when you think about the physical world, that can be really important. Let's pretend that you are part of a research laboratory that's studying DNA, and you have a set of, you have a data set that's being fed into some circuits for analysis, right? And you want to check for reliability. So you want to feed another set of inputs into that circuit, right? Maybe you have sensors, maybe you have analysis equipment that's generating the input data, and you want to test to see if your results are reliable. One of the litmus tests of valid scientific method is the ability to duplicate or replicate experimental results. So I'm just talking through an example here of where this would be valuable. It's really important to be able to switch between inputs for data sets in a variety of scenarios. Think of all the different digital devices you have that have selection options, right? I mean, we don't even think about it because on the graphical user interface side, what? Does anyone here have a smart TV where you can select different inputs?
Yes.
I rest my case. I rest my case. Now, is it possible that there's a circuit that's providing, it's hardwired into the smart TV? Yes, it's also possible that it's also implemented in firmware, in software, right? The whole point is that you have a logical function that allows you to multiplex or switch. Now, you're going to find out later in networking that the ability to overlay signals inside carrier waves, there's an awful lot of functionality that ties back to this, this particular, right? Now, the reverse or demultiplexer is also of value. So the demultiplexer or DMUX allows you to work in reverse. Okay. And it's easy to get confused about what that means. And there's an explicit definition for DMUX. I think it's further in the study guide. It's not like you get to determine what the input was that was used based on the output. That's not what working in reverse means. Let's see, DMUX. works in reverse to use a selector input value to switch between multiple outputs. So the focus of a MUX is to be able to switch between given inputs. The DMUX works in reverse, but the selector switch is focused on multiple outputs. Okay. So it's logically equivalent, but it's not exactly in reverse. Okay. So you have scenarios where you have multiple outputs and you want to be able to capture the output of a given pin and ignore all the rest. So that's what a DMUX is. The thing that I want you to understand is that this is a NAND. Can everybody see this?
Yeah.
Yes.
And we have 4 NANDs. So there's 1, 2, 3, and 4 NANDs. And with those 4 NANDs, we can create a MUX, a basic MUX. And you can build almost any logic gate out of NANDs, almost any logic gate out of NORs. And it would seem to be kind of circular, which comes first, the chicken or the egg, right? The thing I want you to understand is that in the materials science, in the physical world where we're dealing with electronic circuits, there are combinations of physical materials that result in the function of a NAND, and then those in turn are used to build ANDs, ORs, and NOTs. So NANDs and NORs, remember in a previous module, we said NAND and NOR are like the subatomic particles that in different combinations result in the different elements, and that AND, OR, and NOT are like different elements, right? So this is the first sense about that that's presented in your textbook, and I want to call that out. Here's a perfect example of how 4 NANDs can be used to create a totally new logic gate. And yeah, so AND, OR, and NOT are basic logic gates with profound implications. ANDs, ORs, and NOTs are ultimately built out of NORs or NANDs, depending on the. NANDs are also used in some solid state hard drives, right? So when it comes to persistent memory for SSD drives, NANDs are part of that mix. So just think NOR and NAND are subatomic particles, and there's a good example of it. Okay. So here's an XOR gate equivalent circuit. I told you there's another website, this link. If you go, I just want to check to make sure this thing is actually working. Yes, it is. Okay. So if you click this inside Blackboard, you might get a misfire. Let me say that again. If you pull up the version of the study guide and view it within Blackboard, and then you try to click the links, it may block you because you're trying to open up another website. The trick is to copy the link and then open a new tab and go from there. If you download the study guide, I don't know if you've run across this, and you click on links, it should open up without a problem, right? Is everybody with me on that?
Yeah.
Yeah.
Okay. It's I may revise all of my study guides so that whether they're viewed in Blackboard or not, they'll just open up a new site, but that means I have to import the content of each module study guide into Blackboard directly and then work active links, and oh my gosh, it's a lot of work. So we might get to that in a later version of the study guides. I'm thinking of converting my study guides into a textbook itself, open source textbook, where you don't have to buy anything going forward. Anyway, here is an alternate version of an XOR, and I want you to notice how distinctly different it is. We have an AND. Notice the teeny tiny little circle here in front of the AND. That makes this a NAND. You don't see the teeny tiny little circle here. Let's zoom in. I just want to call this out to you. So this is a NAND because that open circle signifies a NOT that is universally applied to the output of an AND. That's what makes this a NAND. This is still an AND because there's no NOT in front of it, right? That's an OR. So we have A and B. The input is split so that the A feeds the A input for the OR gate and the A input for the NAND gate. The B input for the XOR feeds both the B input for the OR, and it splits and feeds the B input for the NAND. Everybody see that?
Yeah.
No.
Right. And then here you have this interesting representation, right? We said bar, A bar and B bar, right? So if you have an AB bar with an AND, that's how they chose to label this pin, right? The plus sign means OR. So this is A or B. And because there's no plus sign here, multiplication is implied. The NOT is applied to both A and B inputs, meaning it's here. So you'll see these different expressions or different conventions represented depending on the website and the company and so on. Q is usually the symbol that's often referred to as out. So you have AB through whatever, but Q is usually the letter they use to represent out in a circuit diagram. Any questions so far?
No.
So I want you to notice the second version of the XOR starts with an OR gate, right? So I'm describing what we just walked through here. If you work up the truth table though, you still get the same canonical expressions, you still get the same output. It's just a different way of building the same logic gate, which begs the question, why would you do this compared to this? How many different logic gates do we have in each case? Well, I have a logic gate here, 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 and here. So what's the total count of logic gates to implement XOR using this method? Hello?
5.
5. How many logic gates do I have here?
3.
3. Which one do you think is more efficient in terms of the use of materials physically?
The bottom one.
The bottom one. Yeah, exactly. Are there cases where you would want something to work, but not so fast? Meaning you'd want some kind of delay between the time you input something and the time you get an output.
Yes.
Yeah, there might be rare cases where a little bit of delay is important. And that's because maybe the next logic gate is processing something and it has to get to it. Let's pretend that in your circuit, there are other things that are processing and it has to, in order for it to work properly, this logic gate needs to wait a little bit before, it's a timing issue. So you have other process going on over here on the right, and in order for that to play out correctly, there has to be a little bit of a delay while some precursors are handled or processed here. It would have to do with sequence. So there are times where you induce less efficiency on purpose for a given reason. And I know that sounds pretty vague, but just let that ruminate for a little bit. In any case, the thing I want you to understand is that this is where people at Intel and AMD and NVIDIA make all their money, right? So folks that get to the point where they really understand how this works, if you finish this course and you really get how this works, you can apply for jobs with Intel and NVIDIA and AMD, and you know, starting salaries are very, very generous, right? When it comes to that. So each of these website links, I want you to spend time, each of these website links. Now, we are going to throw out a new, we have XOR, you've heard of XOR, and now there's XNOR. XNOR. Where XOR identifies, it throws a true, it turns on a light bulb. It says, okay, I got a 1, I got a true, my light bulb is on because the inputs are different. What does XNOR do? Well, I want you to notice when all the inputs are the same, the output is 1. If there are any inputs that are different, the output is false. So it works in a reflective opposite. It's like XOR, except it does the reverse of what XOR does. And wouldn't you expect that with the NOR in the mix? You know, we said that it flipped things, right? So an XOR identifies when inputs are different, throws a true. XNOR is ideally suited to identify when all the inputs are good. If you want a green light to go to launch and everything has to be true, right? Or all your error conditions have to be off, then XNOR is your perfect candidate, okay? This is where I'm going to stop for today. Are there any questions about XNOR and how it's the logical reverse of what an XOR performs? Okay. Now, what can you expect on Wednesday? Well, I'm going to ask. We're going to go over some items on the Module 2 assessment, right? I'm also going to start the class by asking whether or not people can go into the chat window and provide a quick answer. I'll post a question about XOR or XNOR and ask you to respond to me directly. We want to get better at doing this through the month of October, okay? Are there any questions before we clear for the day?
No questions.